Hi, everybody. Today is Wednesday, March 20th. So today we will start session 9.4. And we will also go over the quiz 3. When is our exam? Next Monday. It's about chapter 8, session 9.1 and 9.2. So I hope you can work on your practice exams. And I do realize some of you haven't finished all your homework or haven't get perfect scores on your homework. So I hope you can come to see me more in my office, and you can just bring your laptop and work on your problems. Then when you have questions, you can ask me right away. Okay, everybody? So our goal is to make sure you understand every problem or in the in-class notes, your homework, and the practice exam. Okay, everybody? I know this. I think this is the hardest math class you have, right? And we do cover a lot. And as the topics getting harder and harder, each problem we gonna spend more time on it. Remember last class we had 15 minutes, and one problem we need to spend 15 to 20 minutes on just one problem. And last class we went over 2 examples, then we only have 7 minutes left. So for the last 2 examples, we just look at the solution and talk about the idea. Right, everybody? So yeah, so I hope you understand that our class is challenging and we don't have much time for you to practice in class. So I tried, when we go over the problems, I try to ask you one by one so you are involved and get you think. But we do not have like a lot of time for you to practice in class. So I hope outside of class you can practice more. That's why we have the homework and the solution. And I have a lot of student hours, and so I hope to see you more often. Outside of class, you can ask me questions, and we can make sure you understand every problem in the notes, the homework, and the practice exam. Okay, everybody? Yes, let's try our best. All right. So, section 9.4, Lagrange multiplier. So last time we talked about maximum and minimum is when we have a surface in the space. We can take the first derivative and the second derivatives, and we find the critical points and compute the D, the determinant of the Hessian matrix. And then depending whether the D is positive or negative, and whether the fxx is positive or negative, we determine whether the point is a local maximum or local minimum or saddle point. Do you still remember? But that is the surface in R3. 9.4, Lagrange multiplier, is when we have a constraint on the surface. So let me try to draw the picture here. Okay. So in 9.3, right, we kind of have a surface and you want to find the local maximum. This is what we did in 9.3. Okay. 9.4 is we have some constraint. So maybe the picture is like that. Okay. So we have a surface like that. But there are some constraint. The constraint maybe is a line. Okay. Let's say it's a line on the XY plane. Then it looks like a plane in R3. And with this constraint, this plane cuts the surface or intersect the surface in a curve. Can you imagine you have a surface here and you have some constraint on the xy plane? In the line, it means it's like a plane in space. You kind of cut the surface, you get a one-dimensional curve. So 9.4, Lagrange multiplier, we have some constraint Okay, and you get a curve, and then we want to find maximum or minimum or saddle points for this curve. So we want to find the max or min of this. Is that okay, everybody? So this is one picture. We can have more picture. Like for example, the constraint. So like here, we can also have the same surface. But now the constraint is not a line. It might be a parabola. Like that. Okay? Then what do? You're gonna use a parabola sheet to cut it, and then you get the intersection. It's also a curve, right? It's also a curve. Maybe it looks like that. Can you kind of imagine? Depending on the shape of your constraint, your curve may be different. So now with the curve, can we find the max, mean, or saddle points for the curve? This is a curve in the space. Is that okay, everybody? Yeah. So your constraint could be anything. It could be a line, it could be a parabola, or it could be a circle. Like, for example, if I draw another picture, this is the surface. We can have the same surface. But now, look at the circle. Look at the circle. And then you cut the surface with this circle. Do you see our curve? Look like that. Yeah. And then you can find the max and mean of this curve. This is the main difference about 9.3 and 9.4. 9.3, we only have a surface. And you can talk about the max or min. But 9.4, we have a constraint on the xy plane. Okay, so after you use the constraint to cut the surface, you get a curve. And our question is, can we find the max and min of this curve? Okay, so this is the main difference between 9.3 and 9.4. Okay, so before we go into the method of Lagrange multiplier, we need some knowledge about vectors. So, yeah, you might learn vectors a long time ago in applied algebra, right? So let's review those. The component form of the vector with initial points. P is P1, P2, that's the coordinates, and terminal points Q, Q1, Q2 is, okay, so we draw a picture again. Let's do it here. So let's say we have the point P and we have a point Q, okay, on the xy plane. The vector PQ, okay, the vector PQ, P is the initial point. Q is the terminal points. So the vector PQ has two coordinates, x and y. And you use the terminal points minus the initial points. Okay? So you use Q1 minus P1, that's the x coordinates, and the y coordinates is Q2 minus P2. Is that okay, everybody? We use the terminal points minus the initial points. Okay, so that's the vector, PQ. And the magnitude, or the length of the vector, is the square root of the x coordinate plus the y coordinates. And why is that? Okay, imagine here. Look at this triangle. Okay, look at this triangle. We have the attendance. Thank you. So we know here the change of x is the difference of the x coordinate, which is q1 minus p1. And then here change of y is the difference of the y coordinates, So Q2 minus P2. Then do you see the distance from P to Q is the hypotenuse of the triangle? You know, by the Pythagorean theorem, the distance here, the hypotenuse is the square root of change of x squared plus change of y squared. Yes, everybody? So this is the magnitude of the vector. If a vector has the length is 1, we call the vector is a unit vector. Okay, if the length is 1. Thank you. And then if the length, the magnitude of the vector is 0, even only if v is the 0 vector. So 0 vector, we just put 0 and then we put an arrow on top of 0 to indicate this is a vector. Vector has magnitude and it has direction. Okay, it's not number, it has direction. Okay, so that's the definition of vector. And for vector, we have vector addition and scalar multiplication. So if we have two vectors, u and v, when you add them, you just add the corresponding coordinates, respectively. Right, everybody? And when you multiply them, so if you multiply the u vector by k, what do? You kind of distribute. You multiply all the coordinates by k. Do you still remember these? Okay, let's do example. So we have u, negative 2, 5, and v is the vector 3, 4. Part A, what is 2u? So 2 times the vector u is, let's see, blank? What's the first coordinates? 2, you multiply. Oh, so that'd be -4. Yes, -4. And the second coordinate, Stephanie. 10. Right, everybody? Okay, and then we continue. Part B. Yeah, that's it for part A. Part B. V minus 3u. V is the vector 3, 4. And we subtract 3 times u. U is negative 2, 5. Great, everybody? We do the operations. Look at each coordinate. We do them separately. Look at the first coordinate. Do you see the first coordinate? We have what? 3, and then minus 3 times negative 2. Can you see that? The first coordinates? When you look at the first coordinate, you kind of hide the second coordinate. What's left? 3 minus 3 times negative 2. So write it down. 3 minus 3 times negative 2. Right? And the second coordinates, you have what? 4 minus 3 times 5. Yeah? You kind of hide the first coordinate. What do you have? You have 4 minus 3 times 5. Yes, everybody? Okay, let's see. The first coordinate, Mackenzie, what do you have? Yes, very good. The second coordinate, Sarah, what do you have? Four minus 3 times 5. Yes, negative 11. Yes. Right, everybody? Mm-hmm. So this is part B. Good. Now, it's your turn. Part C. So you find u plus 2v first. Okay, so find this first. U negative 2, 5 plus 2 times 3, 4. Okay. What's your first coordinates? So, yeah, negative 2 plus 2 times 3 is 4. Your second coordinates? 5 plus 2 times 4 is 13. Good. Right, everybody? Okay, so this is the vector. And now we compute the magnitude of the vector. So the magnitude u plus 2v is the square root of each component square. So 4 squared plus 13 squared. Okay, I need your help. So use your calculator. What's 4 squared plus 13 squared? Thank you. Yeah, square root of 185. Okay. If let's see. Yes, part D, we're gonna draw the picture. Let me also ask you, how do we find like a unit vector in this direction? 2 plus 2v. So a unit vector in this direction will be the vector divided by the magnitude of the vector. So this is the unit vector. All right. So, or maybe I can put it here. So your unit vector in okay, maybe it's a unit vector of u is you use u over the magnitude of u. So then the magnitude of the unit vector is gonna be magnitude of u over this is the magnitude of u. So you get the cancel out, you get 1. Okay. Now let's draw the pictures. Okay, so we have the x axis and the y axis and the 0. Part A, the 2u. Okay, 2u, we have negative 4 is the x coordinates. So let's say this is negative 4, and then the y coordinates is 10, right? And we put a dots here connected from the origin. So this is 2u. This Is that okay, everybody? It's like how we plot the points on the xy plane. We just connect them with the origin. We get the vector. And how about the part B? 9, negative 11. So let's say this is 9. And let's say that's negative 11. So you plot the sphere, right? And you connect it with the origin. Okay, so connect like this. So this is part B. V minus 3u. Okay, 9, negative 11. And then the last one, let's see, the last one. U plus 2. Oh, eh? Let me see. Oh, okay. Yeah, part B. We draw U and V. I missed that. And then we draw 2U and V minus 3U. Yeah, we did that. But I forgot to draw U and V. So U, what is U? Negative 2 and negative 2 and 5. So which is this point? So this is U. Can you see the difference between U and 2U? They're the same direction, right? But the magnitude of 2U is double of the magnitude of U. Okay, but they're in the same direction. So you can imagine, if you multiply a vector by a positive scalar, you get a longer or shorter, but in the same direction. If you multiply a vector by a negative scalar, what do? The opposite direction, because it's negative. Okay, and V is 3, 4. Okay, let's use blue color. 3, 4. Where's 3? Like here's 3. 4 is a little bit smaller than 5. So connect them. This is the V. So far, so good? Yeah. All right. Okay, and the facts. Oh, the vectors U and V are parallel if and only if U is the multiple of the V, okay, or a scalar number times V. If the number is positive, then U and V are in the same direction. If the number is negative, then they're in the opposite direction. Okay, so this is the facts. Okay, so that's what we learned before. Next, gradients. What is gradients? Given a function z equals f of xy, the graph is a surface in the three-dimensional space. For example, this is a surface, right? It's a surface in the three-dimensional space. Then the vector, the x coordinates is the partial derivative with respect to x. The y coordinate is the partial derivative with respect to y. This is a vector. And the notation, you kind of use a upside down triangle. This is the gradient vector. Okay. So the gradient, like upside down triangle, F, AB. This is the gradient vector at AB. And it is denoted by the symbol, like upside down triangle. And this is a vector with the coordinate are the first partial derivatives. Okay. Now we will now look at several functions along with their graph and gradient plots. Do you see this is a vector in R2? You have two coordinates, so it's a vector in R2, right? And every point AB, so your partial derivative respect to x is going to be a function of x and y. And your partial derivative with respect to y is also a function of x and y. When you plug in different values of a, b, you get a number, right? So every different point of a, b, you plug in this, you get a number. And depending on, so you get a coordinate, an order pair, right? Order pair corresponds to a vector. And if you're, and you can also see the direction, okay? So this is one example. You, like, when you plug in, you find the first partial derivatives with respect to x and with respect to y. And with the different points, you plug in those two functions, you get a vector. And you can draw the vectors. But in order to have the picture look nicer, we usually scale the vector. So unlike, this is the actual vector. But do you see it's so long? In order to have the picture look nicer, you don't draw the actual vector. You kind of scale it so all of them is like shorter. But then you can still see this vector, like in the middle, is longer magnitude than this vector here is like shorter. Okay? So we scale the vector so they're not cross each other and messy and look nicer. Okay, so here are some guiding questions you should ask yourself as we look at those examples. So what can we say about the directions of the gradient vector? What can we say about the magnitudes of the gradient vector? And how is it relate to the level curves of f? So this is one example. Okay, we have the surface. And look at the picture, this is there we have a maximum here and or local maximum, and we have a local minimum here, right? And from the picture, you can see the red color means the surface, the point here is higher. And then the blue color, you can see the point there is lower. And you see from the picture, like this is higher, this is max, and this is lower. Okay, so this is the surface in R3. Oops, what happened? Okay. And how about the gradient fields on the XY plane? Okay, on the gradient fields, can you see the arrows? Look at the red color, corresponds to the red color. Do you see the arrows pointing inside? And do you see on the horizontal line, do you see the arrows going to the right? And on the blue one, do you see arrows coming out? So arrows, the directions, actually point to where the function increases. That's why, here, this is the highest point. So all the direction, the f increases. So all the arrows point inside. Yeah. And the blue one, do you see this is the local minimum, and then when you follow the direction where the f increases, the arrows is pointing out. So we can see that the direction of the gradient vectors points to where f increases. Okay, so that's the direction of the gradient vector. It points to where f increases. How about the magnitude? Do you see here like the local max? The f increase slowly or kind of at the critical point at the local max, your slope is 0, right? So in this case, the magnitude of the gradient vector, it corresponds to whether f increased rapidly or slowly. If the function increased slowly, your gradient vector is short. Okay? If your function increased faster, your gradient vector is going to be longer one. Yes. So this is what we can see from the picture. And how does the gradient vector related to the level curves? Okay, do you still remember what level curves is? let z, okay, you let z be different numbers. Like z is 0, z is 1, and z is -1, okay? And you get a lot of horizontal plane, right? And you cut the surface. So level curves, maybe like here you get a line, and then here you get a lot of circles. Here you get a lot of circles. Can you imagine, everybody? We cut it. And then in the 2D picture, you can see the level curves like that. Can you imagine, everybody? Can you see the vector is actually perpendicular to the level curves? Yes. So we can see that the gradient vector perpendicular to the level curves. Are you okay with that symbol? Perpendicular. Yes. Okay. This is one example. Any questions so far? All good? Okay. We're gonna look at more examples. So look at this example. Do you see the function f is a plane? Yeah. So your gradient vector is in fact the same vector, right? It's a constant vector. So it points to the same direction. And it points to the direction where the function increases. And level curves is just a bunch of lines. Do you see the gradient vector is perpendicular to the level curves? Yes. So this is the gradient vector. How about this one? Z equals to x squared. Do you see how it has no y? It means the surface is parallel to the y-axis. Okay, it doesn't care what the y is. And then when you draw the gradient vectors, then this is what you get. And do you see this side? The function is increasing, so your arrow is going out. And level curves, you get a bunch of lines for the level curves. And do you see your gradient vector is perpendicular to the level curves? And if your f increase slowly, your gradient vector is short. If your f increase rapidly, then your gradient vector is long. Right, everybody? Yes. This is another example. You have the surface, the paraboloid. This is the surface. And you can look at the gradient vector. Because the f increases when you go bigger, outer. So that's why the gradient vector is pointing out. And near the origin, the function increases slowly, so the gradient vector is short. Outside of the origin, when you go further away, your function increased rapidly. So your gradient vector becomes longer when you are away from the origin. And level curve. Remember level curve? You cut this into smaller pieces. You intersect it with the different horizontal plane. You get a lot of circles. And we can see the gradient vector perpendicular to all the level curves. All right. So summary. Okay. Oh, something's wrong here. Okay. So can I have this back? Okay, yes, I have this back. So summary of the basic properties of the gradient vector. Suppose the gradient vector is not the zero vector, because if it's zero vector, you cannot talk about the direction. There's no direction. It's zero, right? Okay. If it's not zero, we can talk about the direction. The direction, it points to where f increases most rapidly. And it's also perpendicular to the level curves. You can see those from the picture. And the magnitude is large when the level curves are close together. Okay, close together means f increase rapidly. Okay, so level curves are close together. It means f increases rapidly. Do I spell it right? Rapidly? Yeah. Okay, good. And the magnitude is small when they are far apart. So the level curves of far apart means F increases slowly. Does that make sense, everybody? So if you have a picture like this one, and this is so close, or here is so far away, let's imagine. Let's say it corresponds to C is 0 and C is 1, 2, 3, 4, 5. If they're so close to each other, oh, you see the lines increase so quickly. But if they're far away from each other, oh, you see the F increase slowly. Yes. Okay, so that is the gradient field. Okay, and additional facts, the negative gradient vector points in the direction of the maximum rate of decrease of f. Okay, so when it points, the gradient vector points to where f increases the most fastest, and then the negative will be decrease fastest. Okay, that's the idea of the gradient vector. Now, look at this example. Let's talk about how do we find the maximum and minimum of a surface with some constraint. Okay, so suppose we want to find the absolute max and min value of the function 3y minus x on the circle. So we have, this is the surface, okay? This is a surface in R3. And we have a constraint. Okay, constraint is a circle. In other words, we want to optimize the function subject to the constraint. Okay, so we can draw a 3D picture, and we can also look at the 2D picture. Let me give you an idea. So a 3D picture, I don't know what the plane look like, but I know it's a plane. Let's just draw a plane like that. Is that okay, everybody? And you have the constraint is the unit circle. So you use the unit circle and cut the plane. Do you see what happened? It kind of intersects the plane in an ellipse. Oops. Can you kind of imagine you get an ellipse, a curve, and our goal is to find the max and min of this curve. Okay, yes. For example, your function may represent the temperature at the points in the xy plane. Therefore, optimizing the function subject to the constraint means we're looking for the hottest and coldest points on the unit circle. Okay? So this is what it means. The following figure shows how the constraint, the fixed circle, and some level curves of the function f. The parallel lines are the level curves. Okay. And based on the figure, we answer the following questions. Okay. Are there any points on the constraint at which the f equals to 4? No. See, this is f equals 4. It does not intersect the circle, right? So the answer is no. 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 So here we're still trying to understand how the gradient vector working with the max and min of the constraint. So after we do this, we have a formal method we set a system of equations to solve it. Right. Yeah. Okay, so but right now we're still trying to understand why that method works. Okay. So part B. Are there any point xy on the constraint at which f of xy equals to 2? Yeah, we have this point and this point. Yes, there are 2 points. Right, everybody? And are there any points on the constraint such that f of xy is negative 5? No. See, negative 5, we don't have any intersection. Okay? Are there any points on the constraint at which f of xy equals negative 3? How about negative 3? Yes. Let's use different color. Yes. And we have 2 points. Right, everybody? So, we can now estimate, even estimate the max and mean value of the function on the constraint. Look at this. This is what? 3, right? So the biggest number, the biggest f values will be slightly bigger than 3, but not reach 4. I would guess what? 3.2. Do you agree? Yeah, and this is 4, this is 3, and then here is like 3.2, 3.3, 3.1. 3.1? Yes. So I would say the max is around 3.1, 3.2. Close to that. Yes, everybody? And how about the minimum? What's the smallest number? This is negative 3, and this is negative 4. What do you say? Yeah. So the minimum is negative 3.1 to negative 3.2. About like that. Okay? So we got the maximum here and the minimum here. This is what we can see from the picture and the level curves. Right? Okay. Label the approximate location where f attains its max and mean. We already did that. That's the max and that's the mean. We already labeled it. And what is the geometric relationship between the direction of the gradient f and the gradient of the g at the max and minimum points? Okay. At the maximum points, can you see here the level curve of f is the parallel lines? Do you see the gradient vector is pointing to this direction? The gradient of f. Yes. And how about the gradient of g? G is the circle. The gradient at the maximum. Do you see the gradient of g is also perpendicular to the level curves? And you see the gradient of f and gradient of g, they are in the same direction. Right? Can you see that, everybody? Also, how about the minimum? Okay, minimum. You can also see, let's say, if this is the gradient of f, and minimum, do you see the gradient of g? Maybe it's pointing out, but gradient of f, they are in opposite direction, but they are parallel. Okay, so geometric relationship of gradient of f and gradient of g, they are parallel at the maximum and minimum points. Can you see that? Yes, this is special because like other point, you see this is gradient of g and that's gradient of f. Yeah, at other points they are not parallel. It's only at the max and minimum point they are parallel. This is very important. What is the system of equation you would need to solve in order to find the maximum and minimum points? We just said two vectors are parallel if one vector equals a scalar times the other vector. Do you remember that? If the scalar is positive, they're in the same direction. If the scalar is negative, they're in the opposite direction. Therefore, what is the system? The system where we find maximum and minimum points are gradient of f is lambda. By the way, this is a Greek letter called lambda. Have you seen this before? Lambda. The Greek letter lambda. Times the gradient of g. So this is one formula. And another formula we need is the constraint g. The xy must be in the constraint. Okay. So let's say the constraint, in this case, the constraint is g is x squared plus y squared. So the constraint is g equals to 1. Okay? Yes. So not 0, in this case is 1. This system is called the Lagrange system. And the lambda is called the Lagrange multiplier. We set up the system and solve it for xy. And usually we don't need to solve for lambda, okay? But sometimes we might need to solve for lambda in term and then solve x and y. So it depends depending on the system, okay? Okay, so this is the method of Lagrange multiplier, and this is how it works. So answer your questions. When you see a problem like this, you don't have to go through all of that. You just set up the system and solve the system and find x and y. Okay? All right, so let the object function be f. Any constraint function, we call it g, be differentiable on the region of R2 with the gradient of g is not 0. On the curve, g equals to 0. So usually the constraint g, if you have a constraint, we define the g be the left-hand side minus the right-hand side. Then your constraint is always g equal to 0. So to locate the maximum and minimum values of f subject to the constraint g equals to 0, we follow the following steps. We set up the system with two equations. The gradient of f equals lambda times gradient of g, and then the constraint g equals to 0. We set up the system and we solve the system. And then among those values, we plug in f. The largest value will be the maximum values, and the smallest value will be the minimum values. Okay, so after you solve the points, you can then plug in the f to find it. Now, we work on that example. Oh, okay, only 2 minutes. Maybe let's set up the system. Okay, am I not able to solve it and finish that? So set up the system. Our f, what was our f? 3y minus x. Yes, everybody. And our g is x squared plus y squared. I would like to define g be the left-hand side minus the right-hand side. So, because the constraint is x squared plus y squared equals 1. So I use the left-hand side, x squared plus y squared, and subtract the right-hand side, which is 1. Okay, so we have f and g. Now follow the system. Okay, the system, which is right here, we need to find the gradient of f and the gradients of g. So gradient f is the vector fx, fy. Partial derivative with respect to x. What's the partial derivative of f with respect to x? Derivative of 3y is 0. Derivative of negative x? Derivative with respect to x. Negative 1. Yes. So it's negative 1. And then the partial derivative with respect to y is 3. Yes. That's the gradient vector of f. Let's continue next class. And next class also remind me to go over the quiz and quiz mistake and solution. Yes. Okay. I hope next class we have more students. Yes. And we can go over the quiz together. And please work on your practice exams and homework. I hope to see you more in my office hours. Or if you're not available, you can always email me. We can set up a time. Mhm. Okay, sounds good.
My classes.
Yes, sounds good. Bye. Have a good day.